Okay, this video is going to quickly show us how to do a DC sweep here. This allows us to sweep a voltage source from a start value to an end value in a particular number of increments, and it also allows us to create a plot with that. That last thing I just did there is I was adding another net alias, which we talked about in a previous video here. I just forgot to add it into the circuit here. So what do we have here? Standard non-inverting amplifier, gain because of R1 over R2 plus 1, so this would be 4.3 gain, powered by plus or minus 5 volts. This is just a standard 741 op amp. Great to learn on, not very good as far as industrial and commercial applications, but good op amp to learn on. So we want to do a DC analysis of this. I want to sweep this voltage supply. So what I'm going to do is I'm going to first create a new simulation program file, and I'll call this DC sweep. And of course it brings up here. Now by default, anytime you create a new simulation program file, it's going to be a time domain transient. But well, drop down menu, we can say, oh look, there's 4 different options here. We're doing a DC sweep. Which one do you think we might select? Obviously DC sweep. Now there's these primary, secondary sweeps, some of these other things, Monte Carlo. For now we're just going to be doing primary sweep. We'll look into some of those other advanced features later on. But then what we have to do is we have to specify the voltage source we want to sweep. And so if I go here, we can see that the V3, that's the voltage source I want to sweep. So I'm going to say V3. And then we need to enter a start value, which will start at 0. We'll go to 2 volts. And then we'll do an increment of 0.1 volts. Now you could change those. You can make those increments smaller, but you have to be careful. You don't want to make them so small that there's just tons of computations the machine has to do, because it's going to simulate every single value there. We can also choose linear or logarithmic. Logarithmic is sometimes useful depending on what you are simulating, but often we will be doing linear ones for DC sweeps. So we just click on OK, and we have it set up. I'll go ahead and attach a voltage probe here on the output, and I will run the simulation. Then my simulation window is opening up here, and we can see we get this nice little green curve here. Now we shouldn't be surprised about this. We'll talk about how to get some exact values here in a second, but you can see we got a gain of 4.3, so if we look at 0.2, we should be at 0.86 roughly, and we can see right here is 1 volt, here is 0.5 volts, and this is right where it'd be. So yeah, that looks like it's roughly 0.86. And you can also see at the bottom of my screen there's an X and Y, and it's actually telling you what the X and Y values are and where your cursor is. Now we should also notice here as we go up here, we're saturating. And this is a property of op amps that we absolutely know about. If we remember back from circuits 1, if we had an input of 1.4 volts, a gain of 4.3, that's going to be above the power supply of 5 volts. And so in circuits 1, we of course said it would saturate to 5 volts, but now we're actually dealing with real devices as opposed to ideal op amps, and so it's not going to go all the way up to 5 volts. It's going to go to something less than 5 volts because the op amp actually needs voltage as well in order for it to operate properly. There's transistors and other things in there that you have to bias with voltages. Alright, so that being said here, we get an expected result here. We have a nice straight line. If you computed the slope of this line, which maybe we'll do here in a second, you'd get the slope here should be what your gain is. So let's go ahead and talk about how you can perform some measurements here on this. So trace, evaluate measurements. Well, first off, let's maybe see what is the actual output at a particular value here. So if I want to know what the output is at 0.2 volts, for instance, I could do evaluate measurement, and then I'm going to scroll down here and see there's this y at x. That's basically going to evaluate, and now it has one x value. That 1 basically means you need to put in what it is that you're wanting to evaluate. So I'm going to put y at x. Now this is why I labeled the net as an out. V stands for voltage, and this is the net that it will look at the voltage on. So I'm going to say V at that, and then I'm going to say, okay, well, what voltage do I want to evaluate the output at? And I'm going to say 0.2. And then it throws up here. It's throwing up some other ones that I had done in a different simulation here. I can delete those here. And you can add a new, but we can see here Y at V out, it's getting me 806.3 millivolts, which of course is what we should expect. It's a little bit higher than that 4.3 gain that we had said. But again, this is actually a real simulation, not theoretical results. Now, of course, I could change this here. For instance, I could see what it is at 1. Oh, that's 0.1. Let's do 1.0, 4.3 volts. And we could see what it is at 1.4. And again, we can see that it's saturated at the 1.4. And as I said, the saturation voltage is going to be less than that 5 volts, so 4.81554. Now, some other things you can do here is you can turn on cursors, and if you go from trace cursor, you can display. Then if you left click, it's going to put on a set of cursors, and if you scroll down in the bottom right here, you can kind of scroll over here, and the red ones, you can see it's giving you, the top is the X value and the bottom is the Y value. And you can just hold your left mouse button in and drag it left and right. But what you can also do with this is we can, for instance, right click and we get another set of axes there. And now it's going to do Y1 minus Y2. So I'm getting negative numbers right now. But I could move this to the right, move this, oops, right click to move the other one. I could move this to the left. Then you get positive values here. And of course, you could actually just take these two numbers here, divide them to get your slope, to get your gain. Another thing you can do on these is freeze the cursors so that they don't keep moving. And there is also a way to turn these markers on as well. And I keep messing up here. So let's see here, trace. Where's that one? Freeze. And so now these traces won't be moving left and right, so that you don't have to worry. You can right click on things and get back, and so you can do mark data points, other things of that nature. So let's talk about maybe how we could see what some of the other evaluate measurements are. So there's lots of ones in here. Bandwidth, center frequencies, those are going to be things we're going to be looking at in filters. High pass cutoff, low pass cutoff, again, we're going to look in filters. Duty cycle is going to be something important when we start looking at PWM signals. We've got fall time and rise times, something called gain margins. We can compute periods, which from periods you could do a frequency. There's pulse width, rise time, slowing time, slew rates, all sorts of things that you can evaluate. So there's a whole host of things we can do here. So I'll just hit cancel on that, and that's where we'll end this video. So you can do this nice DC sweep here. We can get values here to be able to compute slopes and get the actual gain by looking at this straight line.